Okay, part 2 of 7-6. Thank you, Allison, for noticing. It stopped recording. Sadly, I don't know where it stopped recording.
I think it was just a second ago.
Just then? Okay. Okay, so this is our equation for compound interest. Let's use it in the next example here. Okay, if we look to the left just a second, and I know it's kind of curvy. Okay, financial advisor. Financial advisors help people plan their financial futures. A good financial advisor has mathematical, problem-solving, and communication skills. A bachelor's degree is strongly preferred but not required. Just be very good at what you do. I have a cousin who is one of those. Okay, Maria's parents invested $14,000 at 6% per year, compounded monthly. So what's N going to be? 12. Good. How much money will there be in the account after 10 years? Well, we're going to start off with our compound interest formula. Okay? So we're starting off with 14,000. That's the principal. That's what she had at the beginning. Times the quantity 1. That's going to include our principal amount at the end. Plus, there's your rate divided by n, the number of compounded times. Raised to n times t, well, after 10 years, but times 12 because it's compounding monthly. All right, so we plug that in, 1.005 raised to the 120th power, then times 14,000. So after 10 years, she would have approximately, I'm assuming you can plug that into your calculator now because we've been practicing, $25,471.55 after 10 years. Okay, so now, ¿qué hora es? 11:03. Okay, so we have a little bit of time left. Now, let's go ahead and let's do, I don't care that you see the answer, let's make sure you can get the answer. Determine the amount of investment if $300 is invested at an interest rate of 3.5% compounded monthly for 22 years. Okay, so $300 for 22 years. So we're going to use our, let me see, I'm trying to, well, let me just get a different piece of paper. All right, so here's our formula. A equals the principal times 1 plus r over n to the nt power. Now, so our amount in the end, her initial amount for this activity right here is $300, right? So $300 times 1 plus the rate of 3.5%, so 0.035 divided by, and it's compounded monthly, so 12 times, or 12 times 22 years. Okay, now, so there's going to be our formula, 301 plus the rate divided by 12, that's n, to the nt, 12 times 22. So we're going to plug that in. Let's look at what that would look like on your calculator. Well, that light is something else, isn't it? Okay, so here we go. So we're going to take 0.035 divided by 12, and that is 0.00291666 whatever 7. So that's all sixes are going to go out forever. So that is kind of a weird one, plus 1. Okay, so that's what's going to go in, and let's round it to the nearest 10,000th place just to be as accurate as possible. So 300 times 1.0029 raised to the 12 times 22. 12 times 22 is 264th power. Okay, now if we do that, let's plug it into our calculator. So there's our equation. So we're going to have 300 times parentheses 0.1 whoops, 1 point, sorry, 0029. They may have not taken it out that far, so we may be just a little bit more accurate than them, but 264. Okay, so we've got approximately $644.37. What did they get? $647.20. What do you think that they did that I did not do? What did they do here, do you think?
They probably only did it to the thousandth place.
Yeah, they probably rounded it. So let's do that and see if that's what we get. Okay, so 300. So ours would actually be more accurate. I'm going to tell you a bank, if you're going to have an investment, they are not going to give you any extra money. So they're going to round it way out, to be exact. Okay, times 1.003 to the 264th power. Well, 661. They got 647. Yeah.
What they did was they took the 1.00291666667.
Mm-hmm.
They did the full number.
Oh, full number. Okay. Well, that's smart move, McGroove. Okay, they were even more accurate than us, huh? So 300 times 1.00291667, that raised to the, and that's technically not even the full number, right? Because this is only as far as my calculator can go. Okay, to the 264th, but it would give you to the right penny, so it doesn't really matter. Okay, so that's correct. Good job, Grantlin. Okay, so $647.20, and that's what we got there. Good job. Okay, now the last thing we're going to talk about is exponential, decay. Okay, so we're talking about growth, we're talking about decay. In exponential decay, the original amount decreases by the same percent over a period of time. So remember, that's going to look like a graph curving downward because it's going to get closer and closer to 0, right? It's going to approach 0, but never get there. Okay. So exponential decay, and then a variation of growth equation can be used as a general equation for the exponential decay. So it looks very similar to the original one we had for exponential growth, doesn't it? Y equals A times the quantity 1 minus R instead of plus R to the t power. Okay, things that decay, we talked a little bit about that yesterday, but one thing that's very common, we'll probably read or have an example of it in your homework problems, but one thing is like DDT, and that was something that was used in pesticides, yes, but also spraying, well, yeah, but I'm talking about, what's it called, bug spray, that killed things. Now, I think they have a safer version of it now, but a long time ago, they didn't, and they realized that that was causing harm to people. And so, but there was a certain amount of DDT that was already in our atmosphere that they had sprayed on crops, that we had sprayed on our bodies for bugs, our clothes or whatever. So DDT was in the atmosphere, in the stuff that we have. So over time, the amount of DDT is decreasing, but it's still there. It will never actually be gone. It will get increasingly close to 0, but never actually get there. Isn't that kind of weird? So that's like if you had a jar of water and you put a drop of red food coloring in it. Okay, it would turn the shade of pink, wouldn't it? Just a little bit pink. Now, say we had this whole room filled up with water, or we put that jar, and see, we had a box. It was the size of this room, a big clear glass box. I poured that glass in there. So that would kind of run everywhere, but it would still have that red food coloring. And even if I filled this room up with water, it would get less and less per square inch, wouldn't it? But would it ever go away? Could we ever get all of the red food coloring out? No. See how it runs infinitely close to 0? Getting less and less per square inch, but never crossing 0. Okay, so that is what we're thinking about with exponential decay. All right. So let's look at this example that they have for us right here. Okay, exponential decay. Whoa, we're going even more crookedy. Somehow I have got this all wackadoo. Okay, let me try to straighten it back up. Okay. A fully inflated child's raft for a pool is losing 6.6% of its air every day. The raft originally contains 4,500 cubic inches of air. Now this one, I mean, once all the air is gone, then it is at zero. So this is kind of, a limited exponential decay. Okay, write an equation to represent the loss of air. So this is a decay. When we're losing something, you have to choose if it's going to be exponential growth or exponential decay. Choose one that's losing for exponential decay. All right, so we're going to put in 4,500 cubic inches of air times the quantity 1 minus our percentage. You have to change that to a decimal, 0.066 to the t power. Now, every day. So t is just a day, so that's fairly simple there. Okay, so simplify that. 1 minus that is 0.934. So 4,500 times 0.934 to the t power. Now, here is your equation. Now it says why is the air in the raft in cubic inches after 1 day? After t days, sorry. Okay, and then we have a little bit to do with that equation that's up at the top of the next page. And I will show you that right here. Okay, oh, nope, I will not. It is up there. Sorry, I thought it was on it. It was not. Okay, so now it says estimate. At some point, the little boy or the little girl is going to say, Mama, I need some more air in this thing. I'm sinking. Estimate the amount of air in the raft after 7 days. So we put a 7 up there, plugged it into your calculator, 2,790, and that's an approximation, cubic inches of air, okay? So there we go. Now, I'm going to stop right there. I think you can do this pretty well. You guys are getting this. So everybody enjoy your homework. If you need help, give Sister Killmon a call. Thank you.